One of the first things to recognize is that Git is made up of two different command sets, Porcelain and Plumbing. Porcelain commands are used to interface with Git in the terminal, like the familiar pull, push, commit, stuff like that. Plumbing commands are lower level and reveal the Git internals. Many of these plumbing commands aren't meant to be used manually on the command line at all, but rather to be used as building blocks for new tools and custom scripts. Let's walk through how Git is structured and explore that structure with some plumbing commands to help us get a better understanding of what's happening under the hood. Storage. To understand how Git prevents collisions between different pieces of code, we're first going to explore Git's storage schema. There are only 4 types of Git objects: blobs, trees, commits, and tags. Git stores and represents file content as a blob, short for binary large object. A blob contains a file's contents, but doesn't contain any metadata. To identify unique files without having metadata like a file name, Git uses SHA-1 hashing to identify the blob's contents. We can see this in action by looking at how Git stores the string hello world. First, let's create a text file in our empty directory called foobar.txt that contains hello world. Now, let's calculate the SHA-1 hash for hello world using the plumbing command git hash object. This command takes the string hello world, creates it as an object in Git, writes the object to Git's database, then returns the SHA-1 hash. Even without the file name, you can use that very same hash to find the object in Git's database. If you run git cat file with the -p flag to pretty print, we'll be able to see the string representation of the binary contents of our object. These blobs are how file contents are stored in Git. However, remembering the SHA for every piece of code in your database would be pretty hard. But luckily, the other data types in Git can help us out here. A tree is an object that represents one level of directory information, recording blob identifiers, path names, and bits of metadata for all the files within that directory. Trees build the complete hierarchy of files and subdirectories in Git. They use file names and their identifiers to reference other Git objects, blobs, and even other trees, aka subtrees. We can see all this in the .git directory by running the tree command on the .git folder. Here, in the object subdirectory where our hello world was stored, we can see the 3b is the first 2 characters of our hash. The remaining 38 references the name of the file within that subdirectory. The contents of the file is the object itself, stored in binary format. That's great for file storage, but where does the version control component come in? Well, let's make some more objects: commits and tags. Commits. A commit is an object that stores metadata for each change in the repo, such as commit date, log message, author, the person who originally wrote the code, and committer, the person who last changed the code. Now that we have the file hashed and stored, let's add a commit for our previously created hello world in foobar.txt. We now created our first commit object, which, just like our blob, has an identifying hash. Beautiful. Next, we'll dive into how Git processes your code changes. Git processes and stores your code in 3 places. Occasionally referred to as the working tree, the working area is the actual directory on your file system that reflects the changes you're making, including files not handled by Git, like untracked files. You can make changes without worrying about losing your work if it's already stored in the repo. It serves as the space where developers make their immediate changes, and it's separate from the other parts of the project managed by Git. Also referred to as the cache or index, the staging area is where files are prepared to be a part of the next commit. It's how Git understands what's going to change between the current commit and the next one. A clean staging area, not to be mistaken as empty, is essentially a copy of the latest commit and contains a list of files and the SHA-1 hash of those files from their last commit. When you add, remove, or rename files, Git recognizes the differing SHAs between the changed files and the ones from the repository. The repository in Git contains all of your commits, representing snapshots of what the working and staging areas looked like at the time of each commit. These files are stored safely in the .git directory, allowing you to continue making changes without fear of losing previous versions. You can always check out a fresh copy. It's the core part of Git that holds the entire history of the project, providing traceability and flexibility. Now that we have commit, blobs, and trees, there's one more object that we didn't discuss yet: the tag. Tags are a lot like commit objects, but instead of pointing to a tree, tags point to a commit. It's similar to a branch reference, but it's static. It always points to the same commit, but gives it a more human-readable name. For example, it's easier to read like v1.0.0 instead of the commit hash. Annotated tags, the most commonly used tags, include the tagger's name, email, date, and message, capturing a significant point, like a release version, in a repo's history after a commit. Let's make an annotated tag by turning your foobar.txt into a release version. Then we can verify the tag by running git show with the tag. Great! We can see our commit without having to remember that pesky hash. Branches, unlike tags, are dynamic references to a series of commits. Whenever a new commit is made, the branch points and moves with it. The branch name will always reference the most recent commit on the branch, aka the head of the branch. If you git checkout to a different branch, head moves the pointer to another branch. The head can also become detached if you point it to a specific commit rather than a branch. You might recognize the spooky "you are in a detached head state" message. Let's see what this looks like by first grabbing the hash commit from a previous commit in your foobar.txt. Now we'll check out the latest commit hash instead of a branch. This is dangerous because if you don't do anything, Git will eventually delete any commits made in the detached head state through garbage collection. Those commits are known as dangling commits. To save your dangling commit and escape the detached head state, you can create a new branch that points to this commit, git checkout-b. Now your head is reattached and you're ready to start pushing more changes.